this video, we'll be discussing a very interesting problem, which is Bertown subway. And please take some time to read the question. After that, I'll be explaining the question in detail, and I will be taking you through the approach. So let me first explain the problem very clearly. So first, there is a city, and it has a subway where there are n stations, and for each station I, there is a pi which represents the destination of the train that starts from this ith station. And what's given in the question is that for each station I, there exists only one destination denoted by pi. And for any station j, there exists only one I such that pi equals to j. That means no two stations will have the jth station as its destination. So this is what the topology of the stations is about. Now coming to what's given in the question, that first says about a term called convenience. The term convenience here quantifies the number of ordered bytes such that where the x and y denotes the stations, and this x comma y will be convenient only if a train starts from x the station and reaches y the station. Okay, so what convenience here is that if a person starts at station x, then he can take any number of trains and should be able to reach station y. That number can be 1, 2, or even 0. What do I mean by 0? That a person can start from x and reach the x without taking any train. So that's what the convenient terms quantify. Now coming to the problem, to express it even more clearly in technical terms, what will be given as input are the number of stations n, and for each station we will get the destination. So what essentially it implies is a directed graph where for each node there is only one incoming edge and one outgoing edge. That is, if I be the node, which is a station, then you can only go to one station from the ith station. So there is only one outgoing edge, and there exists only one j, such that I can be reached from this jth station directly. So one incoming edge and one outgoing edge, and this j may or may not be equals to I. So what our task is to, and what we are supposed to find is that we have to maximize the convenience of the city, by following the constraints given the problem. What are the constraints? The constraints given the problem are such that we can modify either destinations of either 0 or two stations. Now, why am I saying 0 or 2? Let's take an example. Let's say let's say this is the entire graph. Now, this is the entire graph we have, where each node represents the station and the each edge represents the source, that is the source station, and to which station the train starting from the source station will be destined to. Now, why did I say that we can either modify 0 or two stations? If we just modify one station, let's say I'm removing this edge and changing the destination of 1 to 6th station instead of second station, then you can see that the second station here has only one outgoing edge and no incoming edge, and the sixth station here has two incoming edges. So what we're supposed to do is, if we change the destination of any one station, then we are bound to change the destination of another station. So now, so what we did is we have modified the graph without violating any constraints. That's why I meant either 0 or two stations, but doing only for the single station will violate the constraint. So this is the output. We have to maximize the convenience of the city by following the constraints given in the problem. Let's see how we approach it. What is the convenience again? These are the number of ordered pairs. But the term ordered here implies that 2, 3 will not be counted same as 3, 2. That is, if a person can go from station 2 to 3 by taking any number of trains, it doesn't mean he can go from 3 to 2. That's why in the problem it is mentioned that the number of ordered pairs. So the number of ordered pairs is that if a person starts from station X, he should be able to reach Y by either taking 0 or more number of trains. So this is what we are supposed to improve. Let me explain few test cases to understand that. Let's take the simplest test case, which is 3, 2, and 3. 3 represents the number of nodes or the number of stations. And here, let's see what each of them represent here. Since there are 3 stations, I'm just plotting the nodes. Now, if you look at the first one, the first element here is 2, meaning if I start from the station 1, the direct station or the train that starts from first station will travel to the second station. That's what is there. And if I go to here, here it represents 1. So these are indexes 1, 2, 3. So the second station, the train starting from the second station will reach directly the first station. Same here, train starting from the third station will go nowhere but stays in the third station itself. This is equivalent to having one uh, outgoing and incoming edge. So this is the graph that is given to us. Now, if we count the number of ordered pairs, if we start from 1, we can reach 2 and we can reach 1 again. And if we start from 2, we can reach 1 and we can reach 2 again. But if we start from 3, we can only reach 3. So currently there are 5 ordered pairs. Now let me just modify the graph so that this number would increase. If I just change the destination of 2 to 3 and the destination of 3 to 1, you can see that we have formed a strongly connected graph. What do I mean by strongly connected graph? For every vertices u and v that are in the graph, there exists a path from u to v. Now, if you just take the graph that we have just formed, this is a newly formed graph. You can see that no matter whatever vertices you take, you can always travel in between these vertices. And since So given a strongly connected graph, how do we find the number of ordered pairs which are connected to each other? That is n choose 2. And since it's an ordered pair, as I said, 2 comma 3 will be different from 3 comma 2. We have to multiply it with 2. And again, we also have reflexive property here where the station can be reached by starting from the same station itself. And these were not counted in n choose 2. So we have n. So these are the number of ordered pairs here, which is 3 choose 2 into 2 plus 3, which is 9. So that's what given in the test case 2. So the answer will be 9. You can see that we have changed the links at only 2 stations, not more than that. Now, what will be the approach? As you can see, the number of ordered pairs will be directly proportional to the connectedness of the graph. So the more connected the graph is, the more ordered pairs we will get. And since we have a directed graph, we bring in the notion of strongly connected components. Uh, I already explained what strongly connectedness means, or if you still have doubt, you can just check it online because it's a very generic concept in graphs. Now, so one thing we know is that the graph has to be more connected. Now, if we already have a graph, let's say graph G with V vertices and E edges, how do we make graph G more connected by changing only 2 edges? How do we do that? Or let's say, let's take an example. Let's say we have two strongly connected components. Let's say 1, 2, 3, and 4, 5. So these are the two strongly connected components we have. In order to make this graph even more connected, what we do, we just erase any one edge in this, and we take an edge from 2 to 5 to any one of the edges in this, and we erase the existing incoming edge to 5, and then we just draw another edge from 4 to 3. If you're confused, I will draw it again. This is what we got. You can clearly see that it is a cyclic one, so it is connected very clearly. What we did, we erased two edges and we were able to connect the two disconnected components so that we get a one strongly connected component. So this is the main intuition behind it. What is the intuition? First one, there are two strongly connected components, let's say C1 and C2. Let's say a graph has two strongly connected components, and what we do, we connect the C1 and C2 and get one final strongly connected component, just like I explained here. Now, a graph can have multiple connected components. Given a graph G with vertices at E and edges E, it can have multiple connected components. How do we choose which two connected components should we join? It's very simple. Whichever components have more nodes will produces more ordered pairs when they are joined. So we find the first two CIs, or let me rephrase it like this. Find CI and CJ such that CI is greater than or equals to CJ and CJ is greater than or equals to rest of all rest of all components. So what I meant to say is find the first two maximus, that's it, and join CI and CJ and count the number of ordered pairs. You don't have to actually join the CI and CJ during the coding, you can just count them. Let's say I have um, X nodes in Ci and Y nodes in Cj. Now, by joining them, I will have X plus Y nodes in the new component. So I'll be having X plus Y choose 2 into 2 plus X plus Y number of nodes. So there's the logic. Now, this is in one single component. In addition to this, I hope you understood the intuition and the approach here. Now the algorithm goes like this. First, get a vector where I, that is ith element of the vector represents number of nodes in ith connected component. Let's say there are C1, C2, C3, three connected components, and C1 has 5, and C2 has 3, and C4 has 4 elements, 4 nodes. So I have to get it, I have to somehow get this vector finally, and then find the first two maximas in the vector. Let's say X and Y with the first two maximas in the vector. Now initialize the answer to X plus Y choose 2 into 2 plus X plus Y. Now iterate through the entire array or vector if vector of I equals to X or vector of I equals to Y, then just continue without counting them because we have already combined the first two maximum components into a single component and included their ordered pairs in the answer already. Else, just add answer plus or equals to vector of I choose 2 into 2 plus vector of I. And finally, output will be answer. Now this is all fine, but how do we get this array? How do we know? How do we actually know number of nodes in each connected component? Or per se, or just say number of connected components itself. For that, we use very generic algorithm in graphs, which is Codeforces algorithm. Assume this as an algorithm like a black box, which takes a graph as input and outputs this vector we want, where each element represents the number of nodes in that connected component. So there's the logic.